Hello, and welcome to Section 4, Sequence Types. We've laid the groundwork by covering single data values, the numbers and booleans, and now we're ready to move on to the first great challenge and huge asset of Python: collections of data. 1. What is a sequence? A sequence is a collection of items where each item is stored in a specific order, and each item can be accessed by its position or index. Think of a sequence like a train. Every car is connected in a line, and you can point to the first car, the second car, and so on. Unlike a single int or float, a sequence allows us to group related pieces of data together. Two types we will cover. In this large and critical section, we will learn the three most important built-in sequence types: strings, lists, and tuples. We'll also cover sets and the incredibly important dictionary, which is a mapping type but often taught alongside sequences. We'll start with strings. A string is simply a sequence of characters used to store text. We'll learn how to create them, access individual characters using slicing, and modify them using various string methods. Next, we'll move to the list. Lists are incredibly flexible and are used to store multiple items of potentially different data types, and they are fully modifiable. Finally, we'll study the tuple, which is similar to a list but has a crucial difference. It is immutable, meaning it cannot be changed after creation. We'll compare lists and tuples to know when to use each. As we explore these types, we will consistently use three key concepts: indexing to access a single item, slicing to access a range of items, and understanding mutability, the ability to change data, versus immutability, the inability to change data. You should learn these sequence types. They are the tools you will use to manage almost all the data in every program you write. We'll start right away with the most common sequence you already use: text. Join me in the next lecture for point 2, create a string, where we'll dive into the world of text manipulation.
Welcome back. We are kicking off our deep dive into sequence types by starting with the most familiar one: the string. A string is simply a sequence of characters, and it is Python's data type for handling text. 1. How to create a string. In Python, the fundamental rule for creating a string is that you must enclose the text in quotes. Python is flexible and allows three main ways to do this: single quotes, double quotes, and triple quotes. About single and double quotes, the most common ways are using single quotes or double quotes. They are generally interchangeable. Why have two options? They help when you need to include a quote character inside your string. For example, if you need a contraction like it's best to use double quotes on the outside. About triple quotes. Triple quotes are primarily used for creating strings that span multiple lines, like paragraphs or blocks of documentation. Two, strings are sequences. The key takeaway here is that a string is a sequence. This means two things: it is ordered, and we can access individual characters using an index. In Python, like many languages, indexing starts at 0. The first character is at index 0, the second at index 1, and so on. We use square brackets after the string variable name to access a character by its index. Python also supports negative indexing, which counts backward from the end of the string. The last character is always at index -1. This is a very convenient feature when you don't know the exact length of the string. Now that we know how to create a string and access a single character, in our next lecture for point 3, slicing a string, we'll learn how to extract a subset or range of characters from a string. I'll see you there.
Welcome back. In our last lecture, we learned how to access a single character in a string using its index. In this lecture, we're going to learn an extremely useful technique called slicing, which allows you to extract a subset or range of characters from a string. One, the basic slice syntax. Slicing allows you to get a part of the sequence, not just one element. The syntax for slicing is very straightforward, using square brackets and the colon operator. String name open bracket start colon end close bracket. Let's use the string programming for our examples. 2. The golden rule of slicing. When you use slicing, the sequence starts at the start index and goes up to, but does not include, the end index. Notice that we started at O, index 2, and stopped just before our index 5. 3. Omitting start and end values. You can simplify the slice syntax by omitting the start or end index. Omitting the end index. If you leave the end index blank, Python will slice from the start index all the way to the end of the string. Omitting the start index. If you leave the start index blank, Python will slice from the beginning of the string up to the end index. Omitting both, the copy leaving both blank creates a copy of the entire string. 4. Slicing with negative indices. We can also use negative indices, which work great for pulling subsets from the end of the string. To summarize, string slicing is a powerful tool to extract parts of a string using the sub start colon end notation. The key rule is that the end index is non-inclusive. This is just the start. In our next lecture, 4.4, Steps in Slicing, I will introduce a third optional component to the slice syntax that allows us to skip characters. See you there. Welcome back. We've already learned the basic string slice syntax, sub start, colon, end. In this lecture, we're going to unlock the final, powerful component of the slicing operator, the step argument. One, the full slice syntax. The full syntax for slicing includes a third value, separated by another colon, called step. String names sub start, colon, end, colon step. The step argument tells Python how many characters to skip after retrieving each character. By default, the step value is 1, meaning we retrieve every character in the range. Let's use our previous example string, programming. 2. Positive step values. If we set the step value to 2, Python will jump 2 characters for every character it selects. Notice that when we omit the start and end indices, the step applies to the entire string. We can also combine the step with a specific range. Three, negative step values. The most common and useful application of the step argument is setting it to -1. A negative step tells Python to move backward through the sequence. If we use this with empty start and end indices, we reverse the entire string. When using a negative step, you also need to adjust your start and end indices. The start index should be greater than the end index for the slice to work in reverse order. To summarize, the third argument in slicing, step, controls how many characters to skip. A positive step moves forward, and a negative step, especially -1, is the Pythonic way to quickly and easily reverse a string. That completes our indexing and slicing strings. Next up, we'll move on to manipulating text with some useful built-in string methods, starting with how to clean up extra white space in Lecture 4.5. Strip the spaces. See you there.
Welcome back. We've learned how to read and extract subsets of text using indexing and slicing. Now, we begin exploring string methods, built-in functions that perform actions directly on a string object. We start with three essential methods used for data cleaning: the strip methods. One, the problem whitespace. A very common issue when accepting user input or reading data from files is extra whitespace. Spaces, tabs, or new lines attached to the beginning or end of a string. This can cause problems when trying to compare strings or use them in lookups. Let's look at an example. 2. The strip method. The strip method is your primary tool for cleaning up this whitespace. It removes any leading, beginning, and trailing end whitespace characters. Notice that the space between Python and course is preserved. The strip method only targets whitespace at the edges. 3. The specific stripping methods. What if you only want to remove spaces from one side? Python provides two specific methods for this: lstrip and rstrip. Lstrip stands for left strip, and it removes only the white space from the left, beginning, side of the string. Rstrip stands for right strip, and it removes only the white space from the right, trailing, side of the string. 4. Important concept: immutability. It is crucial to understand that strings in Python are immutable. This means that when you use a method like strip, you are not changing the original user input variable. Instead, the method creates and returns a new string with the changes. That's why we must assign the result to a new variable like clean input, or assign it back to the original variable like user input equals user input.strip. To summarize, the strip methods are fundamental for data cleanup, allowing you to remove unwanted leading and trailing whitespace, while lstrip and rstrip give you granular control over which end to clean. In our next lecture, 4.6, few more string methods, we will explore other essential string methods for tasks like changing case, checking content, and finding substrings. I'll see you there.
Welcome back. In our last lecture, we covered the essential strip methods for cleaning whitespace. Today, we're going to look at several other indispensable string methods for common text manipulation tasks: changing case, checking content, and finding substrings. 1. Case conversion methods. Python makes it very easy to change the case of text, which is important for standardizing data. The lower method converts all characters to lowercase. The upper method converts all characters to uppercase. The title method capitalizes the first letter of every word. Two, content checking methods. These methods are incredibly useful for validation. They all return a Boolean value, true or false. Starts with, checks if the string begins with a specified substring. Ends with, checks if the string ends with a specified substring. Is digit, checks if all characters in the string are digits, 0 to 9, and if the string is not empty. 3. Substring finding methods. The find method is used to locate the starting index of a substring within the string. Find, returns the lowest index where the substring is found. If the substring is not found, it returns -1. Replace returns a new string with all occurrences of an old substring replaced by a new one. To summarize, these string methods give you powerful, concise tools for common text tasks, from formatting usernames to validating file types. Always remember that they return a new string, they do not modify the original. That wraps up our study of the string sequence type. Next, we move on to the second and arguably most versatile sequence type in Python, the list. Join me in Lecture 4.7. Create a list. See you there. Welcome back. We've learned strings, which are sequences of characters. Now, we move on to Python's powerful and flexible sequence type, the list. 1. What is a list? A list is an ordered collection of items. Unlike a string, a list has two key features that make it special. Mutable. Lists can be changed after they are created. You can add, remove, or modify elements. Heterogeneous. A single list can hold elements of different data types, integers, strings, floats, and even other lists, all at the same time. 2. How to create a list. To create a list, you enclose its elements in square brackets and separate the elements with commas. A. Empty list and mixed data. You can start with an empty list or create one with diverse elements. B. List of lists, nested lists. Because a list can contain any type of object, it can even contain other lists. This creates what's sometimes called a nested list or a matrix. 3. Accessing elements, indexing. Just like strings, lists are ordered sequences, so we use zero-based indexing and square brackets to access elements. We can also use negative indexing, where -1 refers to the last element. 4. Accessing nested elements. To access an element inside a nested list, you use two sets of square brackets. The first bracket gets the inner list and the second gets the element inside that inner list. To summarize, the list is the flexible container in Python created using square brackets. It is both ordered, accessible by index, and fully changeable. Knowing how to create a list is step 1. Next, we will cover the list's most powerful feature, its mutability, by learning how to add and remove elements in Lecture 4.8. See you there. Welcome back. The defining characteristic of a list is its mutability, the ability to change it after creation. In this lecture, we will learn the essential methods for adding elements to a list and removing them. 1. Adding elements. Python provides 3 primary methods for adding items to a list: append, insert, and extend. Let's start with a list of names. A. Appending, append. The append method adds a single element to the end of the list. This is the most common way to add items. B. Inserting, insert. The insert method allows you to add a single element at a specific index. It takes 2 arguments, the index position and the item itself. C. Extending, extend. The extend method is used to add all the elements from another list or any iterable to the current list. 2. Removing elements. You have several ways to remove elements, depending on whether you know the item's value or its index. A. Removing by value, remove. The remove method removes the first occurrence of a specified value from a list. If the item is not found, it will raise a value error. B. Removing by index, pop. The pop method removes the element at a specified index and returns that element. If no index is specified, it removes and returns the last item. The pop method is useful when you need to use the removed item later, such as when implementing a stack data structure. C. Removing a range, del keyword. The del keyword, short for delete, is a general Python statement used to delete objects, including removing elements from a list by index or by slice. To summarize, use append for the end, insert for a specific spot, and extend to merge lists. Use remove to delete by value, pop to delete by index and retrieve the item, and the del keyword to remove by index or slice. We've covered the core manipulation methods. In our next lecture, 04.09, few more list functions, we will explore other essential list methods for sorting, counting, and finding elements. See you there. Welcome back. In our last lecture, we learned how to add and remove elements from a list. Today, we'll cover the remaining essential built-in list methods that help us analyze, order, and count items within our lists. 1. Ordering and reversing lists. These methods allow you to change the sequential order of elements in the list. Let's define a list of numbers. A. Sorting sort. The sort method reorders the list elements in ascending order, from smallest to largest. Crucially, this method modifies the list in place, meaning it changes the original list directly and does not return a new one. B. Reversing, reverse. The reverse method simply reverses the current order of the elements in the list. Like sort, it also modifies the list in place. 2. Finding and counting elements. These methods help you locate and quantify items. Let's use a list of names to demonstrate counting and finding. A. Counting, count. The count method returns the number of times a specified element appears in the list. B. Finding index, index. The index method returns the index of the first occurrence of a specified element. If the specified element is not found in the list, the index method will raise a value error. 3. Clearing the list, clear. Finally, the clear method removes all elements from the list, making it an empty list. To summarize, use sort and reverse for reordering, count to check frequency, and index to find the position of the first occurrence of an element. Remember that lists are mutable, so sort and reverse change the original list directly. We've now learned the list data type. Next, we move on to its sibling sequence, the tuple. Join me in Lecture 0410. Tuple to learn about this sequence. See you there. Welcome back. We've spent a lot of time on the list, Python's extremely flexible and mutable sequence. Now, we introduce the tuple. 1. What is a tuple? The difference. A tuple shares two key characteristics with a list. It is an ordered sequence. Items have a fixed position, accessible by index. It can hold heterogeneous data types, mixed types like strings, integers, etc. However, the major difference, and the entire purpose of the tuple, is that it is immutable. For list, mutable, and parentheses for tuple, immutable. 2. How to create a tuple. Tuples are created using parentheses, in contrast to the square brackets used for lists. A. Creating a tuple with one element. The comma trick. A common pitfall for beginners is creating a tuple with a single element. If you use parentheses alone, Python treats it as a grouped expression. To make a single element tuple, you must include a trailing comma. B. Tuple packing, parentheses optional. Interestingly, the parentheses are often optional when creating a tuple. The items separated by commas are what defines it as a tuple. This is called tuple packing. 3. Accessing elements. Since a tuple is an ordered sequence, accessing elements is identical to how you access elements in a list or string, using zero-based indexing and square brackets. 4. Demonstrating immutability. Now for the crucial point. If you try to change, append, or remove an element, Python throws a type error. This immutability is why tuples are often used for data that should remain constant throughout the program, such as coordinates or configuration settings. Understanding the nature of the tuple is step 1. In our next lecture, 04.11, Use a tuple, we will look at powerful ways to unpack and use tuples in real-world scenarios, leveraging their inherent structure. See you there. Welcome back. In our previous lecture, we introduced the tuple and its core feature, immutability. Today, we will explore practical ways to utilize tuples, specifically focusing on tuple unpacking and using them for function returns. 1. Tuple unpacking. Tuple unpacking is one of the elegant and useful features in Python. It allows you to assign elements of a tuple directly to multiple variables in a single line. This feature is also commonly used for swapping variable values efficiently without needing a temporary variable. 2. Multiple return values from functions. In Python, functions can technically only return one object. However, by packaging multiple values inside a tuple, the function can effectively return multiple items, which can then be unpacked by the caller. Three. Tuples as dictionary keys. A crucial point about dictionaries is that their keys must be immutable. Since tuples are immutable, they can be used as dictionary keys, which lists cannot. This is ideal for composite keys, such as geographical coordinates. The immutability of the tuple guarantees that the key's hash value remains constant. To summarize, tuples are vital for clean code through unpacking, for handling multiple return values from functions efficiently, and for creating reliable, composite keys in dictionaries due to their immutability. Next up, we will explicitly compare the two main sequence types in Python. Join me in Lecture 04.12, List to Tuple, to see how these types relate and differ. Welcome back. We've learned about lists, mutable, and tuples, immutable. Now, let's explore how to easily convert data between these two essential sequence types using Python's built-in functions. 1. Converting list to tuple. To convert a list into a tuple, we use the built-in tuple function. This is necessary when you want to ensure the data cannot be changed afterwards, like securing configuration data. 2. Converting tuple to list. Conversely, if you have a tuple and need to modify its contents by adding or removing items, you must first convert it to a list using the built-in list function. 3. Mutability in action. Now that the data is in a list, we can use any of the list methods we learned before, such as append or remove. Once all modifications are done, you can convert it back to an immutable tuple if needed, for safety or performance benefits. To summarize, use the list function to gain mutability for modification, and the tuple function to lock down data for safety or use as dictionary keys. We've learned how to use both lists and tuples. In our next lecture, 04.13, List versus tuple, we will directly compare them to help you decide which one to choose in any given scenario. See you there. Welcome back. We've dedicated time to learning both lists and tuples. Now, it's time for the ultimate showdown, list versus tuple. We'll compare their core differences, syntax, and when to use each one. 1. Mutability versus immutability. The single most important distinction is that lists are mutable, meaning you can change them after creation. Tuples are immutable, meaning their elements are fixed forever. Let's demonstrate. We can easily modify a list element. However, attempting the same operation on a tuple results in an error. 2. Syntax and creation. Lists are created using square brackets. Tuples use parentheses. Both support indexing and slicing in the same way. 3. When to use which. Use a list when you need a sequence that will change. Data being collected, dynamic shopping carts, or structures like queues and stacks. Use a tuple when the data must remain constant, coordinates, database records, or composite dictionary keys. To summarize, lists are flexible and dynamic, while tuples are fast, safe, and reliable for fixed data. Choose list for change. Choose tuple for permanence. That concludes our coverage of lists and tuples. Up next, we move on to another sequence type, the set. Join me in Lecture 04.14. Set type. Welcome to a new sequence type, the set. Sets are primarily used to store multiple unique items in a single variable. In this lecture, we'll learn how to create and modify sets and understand their key characteristics. 1. Creating a set. Sets are created using curly braces, much like dictionaries, but they only contain values, not key-value pairs. Crucially, sets automatically discard any duplicate values. An important note, to create an empty set, you must use the set function, as empty curly braces create an empty dictionary. 2. Adding elements to a set. Since sets are mutable, you can add new items using the add method for a single item, or the update method to add multiple items from another iterable, like a list or tuple. 3. Removing elements from a set. You can remove elements using the remove method or the discard method. The difference is critical. Remove will raise an error if the item is not found, while discard will not. To summarize, sets are defined by curly braces, enforce uniqueness, and lack order. Use add or update to add items, and choose between remove or discard for removal based on whether you want to handle potential errors. In our next lecture, 04.15, Frozen Set, we will look at an immutable version of the set, useful when you need a fixed collection of unique items. See you there. Welcome back. In our last lecture, we explored the mutable set type. Now, we introduce its immutable counterpart, the frozen set. This special type combines the uniqueness of a set with the safety of immutability, similar to how tuples relate to lists. 1. Creating a frozen set. You create a frozen set using the built-in frozen set function, passing any iterable, like a list, tuple, or an existing set, as an argument. Like regular sets, the frozen set automatically removes duplicates upon creation, and the order of elements is not guaranteed. 2. Immutability in action. Because frozen sets are immutable, they do not have methods that change their content, such as add, remove, or discard. Attempting to use them will result in an attribute error. 3. Primary use case. Dictionary keys. The main reason for the existence of frozen sets is that they are hashable due to their immutability. This makes them suitable for use as keys in dictionaries or as elements within a regular set, which mutable sets cannot do. To summarize, use the frozen set function to create a fixed collection of unique items. Its immutability ensures safety and allows it to be used as a key in mapping data structures. We have covered lists, tuples, sets, and frozen sets. Up next, we'll explore another built-in sequence that generates numbers, the range type. Join me in Lecture 0-4-16. Range type. Welcome back. In this lecture, we explore the range type, a special immutable sequence primarily used to generate sequences of numbers for iteration, particularly in for loops. It is highly efficient because it doesn't store all numbers in memory. 1. Range syntax. The range function takes up to 3 arguments: stop, start, and step. The most common form is providing just the stop value. If you only provide the stop argument, the sequence starts from 0 and goes up to but not including the stop number. Providing both start and stop defines the starting point, but still excludes the stop value. The optional step argument controls the increment or decrement between numbers in the sequence. 2. Using range for indexing. The range type is extremely useful when you need to access elements of a list or other sequence by index. To summarize, the range type is an immutable sequence that generates numbers on demand, making it memory efficient. It is indispensable for defining loop boundaries and generating indices. In our next lecture, 0-4-17, bytes and byte array, we will examine binary sequence types used for handling raw binary data, like images or network packets. See you there. Welcome back. In the digital world, data isn't just text. It's also raw binary data, like images, audio, or network packets. Python provides 2 sequence types for handling this, bytes and byte array. We will explore how to create them and the crucial difference between them. 1. Creating bytes and byte array. Both types can be created by prefixing a string literal with b, or by using their respective constructor functions. Crucially, they store sequences of integers ranging from 0 to 255. The bytes literal starts with b. Note that when you index a bytes object, it returns the integer value of that byte, not a single character string. The byte array is created using the constructor function. We typically use the encode method on a regular string before passing it. 2. Mutability difference. Since bytes are immutable, you cannot change individual elements. Byte array, being mutable, allows you to change the value of any byte by assigning a new integer between 0 and 255. If you try to change a byte's object, Python will raise a type error. To summarize, use bytes for fixed, binary data and byte array when you need to modify the binary data in place, such as manipulating a buffer or receiving stream data. We've learned the core sequential collection types. Next, we revisit the dictionary type in detail, focusing on its structure and use cases. Join me in Lecture 04.18. Dictionary. Welcome back. We now move to the dictionary type, one of the most powerful and flexible data structures in Python. Dictionaries store data in key-value pairs, which allows for extremely fast data retrieval. 1. Creating a dictionary. Dictionaries are created using curly braces and separating keys from values using a colon. The keys must be unique and immutable, while the values can be of any type and can be duplicated. 2. Accessing elements. Instead of using numerical indices like lists, you access dictionary values by referring to their key, enclosed in square brackets. If the key does not exist, this method raises a key error. Alternatively, you can use the get method, which returns none or a specified default value if the key is not found, making it safer. 3. Modifying elements. Dictionaries are mutable. To change a value, you simply access the key and assign a new value. If the key does not exist, this action adds a new key-value pair to the dictionary. To summarize, dictionaries use keys for lightning-fast retrieval, are mutable for easy modification, and are ideal for modeling real-world objects where data points have descriptive labels. In our next lecture, 04.19, Immutability, we will delve deeper into the concept of immutability and why it is a core feature in Python's design. See you there. Welcome back. We've seen concepts like lists being mutable and tuples being immutable. Now, let's dedicate a lecture to truly understanding immutability, a fundamental concept in Python that impacts data safety, hashing, and performance. 1. Core definition and identity. An immutable object is one whose value cannot change. If you appear to change an immutable object, you are actually creating a brand new object in memory and reassigning the variable to point to it. For mutable objects like a list, its memory address, or ID, remains the same even after modification. For immutable objects like a string or tuple, any operation that modifies it results in a new object with a new memory ID. 2. Why immutability matters. The key reason is hashing. Only immutable objects can be hashed, meaning they have a constant hash value. This makes them eligible for use as dictionary keys or elements in a set, both of which require constant hash values for fast lookup. Since a list can change, its hash value would change, breaking the lookup structure of dictionaries and sets. To summarize, mutable types can be modified in place. Immutable types cannot be modified and are required for dictionary keys and set members due to their consistent hashability. Our next lecture 04.20. Datatypes patient use case. Welcome back. We've learned the core Python data types: numbers, strings, lists, tuples, sets, and dictionaries. Now, it's time to see how they fit together to model real-world data in a use case, specifically focusing on patient clinical data. 1. Defining patient data structure. We will model a single patient using a dictionary, as it allows us to use descriptive keys like name and age. We'll use strings for the ID and name, and an integer for the age. Next, we add the patient's vitals and medication history, which requires sequence types. 2. Using lists and tuples. Vitals, like heart rate and blood pressure, are measured over time and change frequently. We'll use a list to store these records, reflecting mutability. Notice that each individual reading is stored as a tuple, guaranteeing that the blood pressure and heart rate pair remains fixed and consistent. 3. Using sets for unique data. Allergies must be unique. A patient cannot have the same allergy listed twice. Therefore, a set is the perfect type to store this information, ensuring data integrity. To summarize, we modeled complex data by strategically choosing data types: dictionary for structure, lists for mutable history, tuples for fixed data points, and sets for unique constraints. We will continue exploring application-based data modeling in our next lecture, focusing on how lists and dictionaries interact. Join me in Lecture 04.21, Map of Lists Use Case. Welcome back. In our last lecture, we used different data types to model patient information. Now, we will focus on a common and important data structure known as a map of lists, which means a dictionary where every key maps to a list of values. 1. Defining the structure. This structure is ideal for tracking categorized data, like inventory or sales, where you have a unique category key and multiple items belonging to that category. We will use it here to track different types of fruits. 2. Accessing and iterating data. Accessing data involves 2 steps. First, retrieve the list using the dictionary key, and second, access the item inside that list using its index. You can easily iterate through both the categories and the items within each category. 3. Modifying the map of lists. Since both the dictionary and the inner lists are mutable, we can add, remove, or modify items easily. We can also add a new category key with its own empty list, ready for data. To summarize, the map of lists structure provides a flexible and logical way to group and manage related sets of data, leveraging the key-based organization of a dictionary and the ordered, mutable nature of lists. This concludes our sequence types. We now move on to Chapter 5, Special Types. Join me in Lecture 05.01, None Type.